Probablemente podéis dejar esta pantalla.
Sí.
Probablemente podéis dejar esta pantalla.
Sí.
Okay. Good morning. Buenos días. Ohayou gozaimasu. Welcome to this conference of the series of European Japanese conferences. And I will say just some words of welcome to put into context this connection and how it working. The contact with Japan for cultural things is very old, and it goes back to the famous Kamagawa wave of Hokusai, but this is painting. And then in partial differential equations, I remember that when I was studying in Paris, there was a strong connection with Japan because there were many people interested in functional analysis and semigroups and monotone operators. For instance, Professor Komura. And Professor Kato was living in California, was also very well known because of his interest in Navier-Stokes and because of his beautiful inequality that we like so much, Kato's inequality. And then life went on, and I began to be interested in free boundaries and evolution problems, nonlinear diffusion. And the first time I met all of this group of people, community, we call them communities. Community of these people was in a beautiful conference in 1981 in Montecatini, next to Florence. And at that time, I met not only the people, but also the ideas. And the ideas was studying flows with nonlinear operators and trying to understand the regularity and the existence of free boundaries. And I remember Professor Mimura. But also they were interested in reaction diffusion. That was very popular in the States because of the book, for instance, of Smoller. And in that direction, there was a beautiful paper by Professor Giga with the people in Kuran. And so there was a connection that began to be developing in different directions. One of them was reaction diffusion. Another one was maximal monotone operators and semigroups. Another one was interest in fluids. And then there was this new thing that was viscosity solutions. And there, Professor Ishii was very important. And the idea of generating flows that do something in functional space was practiced by Hiroshi Matano. And I remember the first time I went for a time to Japan, I was invited by him, and I was very happy to be in Tokyo and Kobe and Kyoto. And all of this direction made some fruit in the sense of organizing things. We organized in Spain in 1993 the International Conference on Free Boundaries. And there were many people from all countries of the world, in particular Japan. But what is more important, around 2004, thanks to the influence of Marek Fila, which was a very good friend of us, a very friendly person. We organized the European Japanese conferences on blow-up. And the first one was in Bratislava, of course, in 2004. And there were conferences in 2006. 2006 was in Madrid. I was very happy. And we had this, let me give another name of this connection with people in Japan. There was Professor Fujita, was fantastic name. Professor Fujita and his exponent made a very strong influence in Spain. He was here and we had many incidents with him. It was very nice life for a week. And then there were conferences in 2008, 10, 14, 16. And for a time we stopped. And we want to begin now in this atmosphere of the Institute for Mathematics that is called ICMAT, ICMAT we say in Spanish. And we have now in Madrid a wonderful institute that can accommodate many persons visiting from different parts of the world. And one of the organizations was in PDEs, and nonlinear PDEs are very strong in Spain, and we have many contacts, so they decided to have a 6-month program. Inside the 6-month program, there is a special week for Euro-Japanese conference, and I'm very happy that we are reviving the old spirit and having these wonderful people from all countries of the world, in particular our collaborators in Japan, Goro Akagi, and Professor Ishige, and Professor Yanagira, who was in the old time organizing these things with Marek and others. And I will not take more of your time. It's a real pleasure to have people from all countries of the world here around us. And the peace drive of the friendship between Japan and Spain is coming, I remember, it's coming from this famous Kamagawa wave. So it's all thing. And we will try to see if we can prove the theorem during this week. So, 友達はようこそでしょう。Now, Professor Ishige will say some words in part of the Japanese contribution.
Okay. First of all, as one of the organizers, I'd like to thank all of you for participating in this conference. And also, the ICMAT gives a lot of support to us, in particular, participants from Japan. So I'd like to thank ICMAT for the contribution and nice hospitality for Japanese participants. On the other hand, when I received the proposal, this conference from Professor Conforte and Goro Akagi, I saw that this is the next project to Euro-Japan workshop blow up. So I asked this idea to Professor Yanagida and Professor Marek Fila, but then they kindly accept this idea. So this workshop is the next project, the Euro-Japan workshop on blow up. So but as you know, unfortunately, Marek Fila passed away at the end of last April, but we can take his spirit and concept by using this conference, I believe. I will enjoy, I hope you will enjoy this workshop. Thank you.
I think that this will be fit to devote the conference to the memory of our good friend Marek Fila. Okay. We have a pause, so we go next conference.
Yes,
That's
the
it.
time, the technical time to adjust the slides.
Okay. So next first lecture of this conference is Professor Yanagida. I was thinking about how many names penetrated into the folklore mathematics in Spain. I think the most popular one is Professor Cogita. And this conference in Blow Up made much emphasis on his work. He was very happy when he was in Spain. And then, of course, another person who is incredibly important is Professor Campbell. And in this generation, it's a bit more next to mine, maybe Professors Matano, Giga, and Ishii were very popular for different reasons, right? There were different lines, which is very important. Ishii is related to viscosity, and Matano is related to dimensional dynamical system, and then Giga is related to, he has so many things, but this theorem about blow up with Kong was very important. And I don't know if my friend Philippe has any comment on that.
I completely agree. Yeah.
Okay. Okay, so Professor Yanaguina will talk about solutions with moving singularities. Moving singularities is a curious thing that happens in nonlinear diffusion. The singularity in a linear operator normally stays where it is, but in the nonlinear operators, it has a tendency to move around. Once you have a singularity, it does not stay put, it can move. So these moving singularities that they found are very curious, and they are not, in my opinion, well understood. So let's listen carefully to this talk of Professor Eiji. And please.
Thank you so much. Okay, so this talk is based on joint work with Mark Fila and Jin Takahashi there. So actually this work has been completed 1 week before. You can notice that the date here is just 1 week before. And so this is the last email I received from him. And okay, sorry. Actually, I was visiting Bratislava in March of this year for 1 month or so, and then fortunately, we have completed this work almost, and so I stayed there until the end of March, and so I returned from Bratislava to Tokyo on Friday, the last Friday of March, and sorry, Saturday. So 1 day before my flight departure, I went to his favorite beer hall and made a toast, because so he was so proud of this work. And so anyways, it was completed. And I'm very happy to have this opportunity to talk about this work. So I don't talk anymore, because I was earlier given a chance to talk about him a little more tomorrow. Okay. So this is about this equation, the nonlinear diffusion equation, and M is between 0 and 1. So this is usually called the first diffusion equation, because diffusion rate goes to infinity when U goes to 0. Okay? So this is usually called first diffusion equation. But I'm interested in the singular solution, which I mean the solution which goes to infinity at some point. So if you goes to infinity, then the diffusion rate goes to 0. So it's a slow diffusion. Okay? So because of the slow diffusion and the singularity, so the solution can, and there may exist various types of singular solutions. And with the isolated singularity. Okay, let me show you some examples. So this is a simple one. This is a standing stationary solution. Okay, so this is explicitly given in this way. Of course, if m is equal to 1, this is nothing but the fundamental solution of the Laplace equation. But this is the simplest example of a singular solution. So here C is an arbitrary constant. Okay. So this is the simplest example of a singular solution of the first diffusion equation. And this one is a dynamic solution, time-dependent solution, which is explicitly written in this way. Here, alpha is a function of omega and t, where omega is the element of the unit sphere. So omega is the direction from the origin. So it depends on the direction and time as well. And this is a special dependence, which is this as a simple form like this. Then if you substitute this function to the equation, then when the exponent here is 2 over 1 minus m, then everything, many terms cancel out, and then we can get the equation for alpha. So this is the parabolic equation, non-linear parabolic equation on the sphere. And then actually, this more general situation was studied by Vasquez and Professor Vasquez and Winkler in 2011, but somehow it's the simplest way to find the dynamic singularity for the first diffusion equation. So this is a typical profile of the solution. So this is this blue curve is the solution of alpha. So this is just the section. Okay? So this section, the level set may depend on the time and the direction. Okay. So recently, with Marek and his student Makova and Takashi, then we found another type of singularity. So this is the anisotropic standing singularity, which depends on omega. So it depends on the direction. This is in some sense standing stationary. I will say stationary near the singular point, because this solution, this function, does not satisfy the equation, but asymptotically it satisfies the equation. And so, I mean, if you substitute this to the equation, then only higher, very small terms are left. Okay. And now, so alpha can depend on omega, so it's anisotropic. Yes. But the first one is first example, second example, then they were more the first is stationary. Stationary standing solution is rotational symmetric, but this is not. Okay. So this can happen because of the slow diffusion near the singular point. Because near the singular point, diffusion rate is so small. Okay? Because then, if it is not isotropic, then it cannot change its profile, asymptotic profile. Yeah. All right. So also in a few years ago, we found another type. I mean, a moving singularity. So this is given in this way. So the solution U is actually this kind of solution exists only when m is between m is bigger than n minus 2 by n minus 1. So in this case, the singularity can move. So the position of the singularity may depend on time, and also the question here can depend on time. So it's rather flexible. Okay. So this kind of solution exists only in this parameter range, but anyway, this is another type of the singular solution, solution with a isolated moving singularity. And but this solution is necessarily rotationally, asymptotically rotationally symmetric. because so this condition means that the diffusion is slow enough, but not so slow. So this may somehow stabilize the singularity, and the solution becomes rotation, radial symmetric, simply radial symmetric. But if M is critical, okay, suppose M is this critical case, okay, M is just critical, then we can find anisotropic moving singularity. Okay, so this is this new discovery, but only in at this. If M is critical in this sense, then we can find such a solution. Okay, so these are results about the high-dimensional case. And the two-dimensional case was also discussed by Marek, Jean, and Petra Kova and myself, but one-dimensional problem is left open. So today I want to talk about the one-dimensional problem. So one-dimensional means that, okay, it's a very simple equation. And C of t is the position of the singularity. So the solution U looks like this. It goes to infinity when x approaches C of t. But in the one-dimensional case, then the domain, the line is separated into two parts. And we can consider one-dimensional fast diffusion equation with a moving boundary. But the point here is I'm interested in a singular solution. So U is supposed to go to infinity at this point. So this looks so simple, but the difficulty comes from this singularity. Okay. Any question? Are you happy with this? Right. So there are some typical things, explicit singular solution. One is the standing singularity. There is no, okay, I'm talking about positive solutions only. So there is no stationary positive singular solution, but there exists a similar solution. For instance, if M is less than 1, then the solution, there exists a solution which behaves like this way. So the solution starts from the trivial solution, but suddenly it appears a singularity, and it becomes positive, and it becomes bigger and bigger. And so goes to infinity as t tends to infinity, but the singular point here doesn't move. Yeah. Another simple example is the traveling singularity. So if we can find traveling singular solutions, which is sometimes referred to as the semi-waveform solution, because the solution is defined only not in the whole line, only the half line. So the nature of C is the constant, which depends on the speed c. And now the singularity moves with a constant speed c. Then, if h of c is constant and the power here is -1 over 1 minus m, then we can find such a traveling singular solution. Yeah. These are two very simple examples. They are explicitly written down. Then the natural question is what happens for more general motion of the singularity and the more general initial data. The first thing to study has to be the existence of a solution of the initial value problem. Okay, now let's consider initial value problem. This is the equation which is defined for x bigger than c of t. T is positive, and this is the given initial data, which is supposed to be non-negative and continuous. But I'm interested in the singular solution. So the no boundary condition is imposed at the singular point, but I only assume the solution goes to infinity. So this is rather, I would say, mild condition for the solution. I would say it's a loose condition for the solution. So this is a very simple problem, but it's not a trivial question to ask the existence and uniqueness of this initial value problem. So the standard way to study this is to consider the approximate solution from below. So let UN be a sequence of boundary solutions of this approximate problem. So this approximate problem is obtained by cutoff. Okay, so the boundary condition is cut off at the end, and initial data is also cut off at the end. So now this is the regular problem. So it's not hard to prove the existence, the uniqueness of this solution. But the point is that if now the boundary condition is here and solution is supposed to be similar to the CT. So also the initial data is cut off by n. So by the comparison principle, if the solution, the approximate solution must be smaller than any singular solution. Okay. But if n goes to infinity, we expect the singular solution is obtained as a limiting function. In fact, we can, if because the approximate solution UN is motor increasing in n because of the comparison principle. If the approximate sequence is motor increasing with respect to n, so if the sequence is convergent, then it must be a solution which we want. So to show the convergence, what we need is the upper bound, okay, because it's motor increasing. So there's a upper bound, and we can easily find the solution at least one. So this should be a minimal solution. Okay, then actually we can do this one. If COT is non-decreasing, well, this is the essential condition. Okay, if COT is non-decreasing in time, then there is a singular solution of the initial problem for any time interval. Okay? As long as COT is moving toward the right. So to show this existence, I told you that we need an upper bound. So it's obtained by constructing suitable upper solutions. So this is done by using the explicit solutions, which I already talked about. So this UA is the self-similar solution, which has a singularity at A. This UB is the self-similar solution with the singularity at X. Then add the two terms to solutions and define capital U plus in this way, then it becomes a super solution. Okay. This is a simple way to construct to find the upper solution. We did like this. This is the upper solution, which is a singularity at A and singularity at B. And it starts from the 0, but anyway, it goes to infinity as t tends to infinity, but it remains bounded like this picture. Then if you set this function here, upper bound here, then if a solution exists for the initial value problem, it must be below this upper bound. So at least the approximate solution, if it converges, then it must be below this curve. So this is the boundaries is only obtained between A and B, but A and B are arbitrary, so we can just put many upper solution like this way to cover whole line. Okay. Then actually all the upper bound for the singular solution of the initial value problem. So the singular solution must be convergent because there is upper bound. So then there is at least one solution for the initial value problem. And from this construction, we can find only the minimal one, the smallest solution. But there may be a bigger singular solution, of course. But anyway, at least we can find a solution which must be minimal one. But okay, what happens to when the singular point is moving toward the left? I told you the motion of the singularity is essential for the existence. If it moves toward the right, then we can find a singular solution. But if singular point moves toward the left, I mean, it's a moving boundary, moves toward the left, then the approximate sequence is not convergent. In fact, approximate solution goes to infinity between in this interval. For this is the initial point of the singular point, and then it moved toward the left. So this one is smaller than c0. So there appears some interval, and in this interval, it goes the solution. The approximate solution goes to infinity. While in the right side, then there is a bounded solution, but it is the minimal solution of the initial value problem when singular boundary point is not moving. This situation like this. Okay, this is the initially the singularity is here, it moved to the left. Then the solution goes, then no solution, it goes to infinity. So it's sort of burning zone or burning core. But in the right side, nothing happens. Okay, so well, if you fix this singular point here, then we can find a solution. So the motion of the singularity is essential for the existence of a solution, positive solution for these initial value problems. Okay, to show this, again, we reconstructed the lower solution, or even in this range. Okay, so this is the, n is here. This is the approximate solution. Okay, so now it's this is moving to the left. So this point is kept at the n here. So this is the approximate solution, and we can find the lower bound, like lower solution. And this function is constructed rather delicate by the delicate analysis of ODEs and something. But anyway, this sub-solution goes to infinity in this range. So everything is elementary, but actually it's not. Okay, the first guess was really difficult. So we discussed with Marek again and again, and so it seemed to be true, but I don't know whether this is true or not. But fortunately, we found a suitable lower solution of this problem. Okay. Okay, so this is about the initial value problem. Then the next one is about the asymptotic profile of the minimal solution, or about the singular solution. So we found that the singular solution must be, okay, so I'm assuming that the COT is moving toward the right. Okay. And the solution is bounded by this function, this function. The two exponents appear here. This is the same as the order power of the traveling singularity. Okay. But this one is the standing singularity. But the solution must be doing that. When the solution moves to the right, singularity moves to the rightward, then actually this looks like a traveling singular solution near the singular point. So it's rather natural. If it's moving.
What is H?
H is the coefficient of this traveling singular solution. Okay, let me go back to the. Let's see. What this okay. So this is
okay.
This is a constant given this way. So this must be not arbitrary. Yeah. So the leading term is exactly the traveling singular solution. Then again, I will the barrier method to find upper solution. Okay, upper bound. So this is the suitable upper bound. And okay, the solution, okay, this is the point move to the right, or then this solution approaches to this upper bound, but always below this super solution. So when this singular point reaches this point, then the solution must be below this upper bound. So this gives the lower upper bound of the solution. Okay. So this is the self-similar solution. So this is the rate of the 2 1 minus exactly. And on the other hand, well, this is the picture. When the singular solution reaches here, then it's still below this one. So this gives the profile around this singular point. So this will be upper bound of the upper estimated solution. On the other hand, a lower solution is obtained this way. Now, yes. Now this is the let's see. This is about the upper bound. Yes, but this one. Yes, I mean that's the explanation behind this. It's a lower bound. So then now this is the solution. The lower bound is obtained by using a traveling singular solution. Because traveling singular solution is small, something near a singular point. So we take C suitably to come to this point at time tau. Yeah. Then what happens is when a traveling singular solution comes here, okay, this is slightly modified, but the traveling, this is lower bound anyway, then the solution is estimated from below like this. So this gives the lower bound of the solution. And this is the, again, this is the rate for the traveling singular solution. So let's give the profile of the traveling singularity. Okay, how about the uniqueness? This is really a difficult question to answer because the condition and around the singular point is quite loose. Okay. Only, I'm assuming only the solution goes to infinity. It's even a weaker condition than the normal boundary condition. So it's not a question to ask about the uniqueness. But we proved the uniqueness under rather mild condition. So we only needed 2 conditions. One is this one. This one is the initial value goes to infinity at least monotonically near the singular point, monotonically. And the second condition seems to be rather technical, but anyway, initial value and their derivatives are bounded. Actually, this must be bounded above, and this must be just bounded. So this is just a technical condition, but both conditions say that the solution, the initial value does not behave so in a crazy way that it's in the space. Okay. For instance, if U0 goes to infinity in a very oscillatory way, then what we don't know. It's really difficult. But if it's monotone near C0, then we have a uniqueness. But to prove this, we must show that the minimal solution is actually maximal. Okay, so we already know the existence of minimal solution. Then what we have to show is that it's a maximal solution. And so this is how to prove the minimality of any singular solution. Just shift the solution slightly to the left. This way. This is okay. This is the simplest case when the solution is monotone decreasing. If you shift it slightly leftward, then it must be below this one. So, if epsilon goes to 0, then the solution is this blue curve goes to the singular solution, but this must be a minimal solution. So any singular solution must be minimal. Okay, also any monotone decreasing singular solution is maximal if you compare the solution with a slightly shifted solution. So at least in the simple case, when this solution is monotone decreasing, then any singular solution is minimal and maximal as well. So this means the uniqueness of the solution. So in the case when initial value is increasing somewhere, then it's really needs some more technical condition like A2. But in that case, we need to we must care about the behavior solution near spatial infinity. So it makes things a bit complicated, but somehow we need to match the inner solution and outer solution at some matching point by the matched asymptotics. Then we can somehow show that it's a minimal as well as a maximum. Okay. So next, I want to discuss the long-term behavior of solutions. First question is about the stability of the semi wavefront. So we can actually, this was talking wavefront in some sense globally asymptotically stable. That is, if the initial value goes to 0 as x goes to infinity, and if the singular point, the speed of the singular point converts to a constant c, then the solution converges to the traveling singular solution for any initial value. So it's a global, sort of global stability. Of course, this condition is essential. If U0x goes to a constant, for instance, positive constant, it cannot happen. The essential condition is the initial value goes to 0, and it means the solution goes to 0 as well for all time. So for proof, we use a rather standard way to show the convergence. So find a super solution like this one, a sub solution like this one, the sandwich. Then, as much as possible, and if so, this means PT here and here, QT here and here are decreasing function. So this means this region here is getting narrower and narrower, and if the gap remains for all time, then it contradicts the maximum principle. So this means that the solution must be sandwiched by these two functions and go close to each other. So this means the global stability of the traveling singular solution. Actually, this problem, for this problem, the solution is very stable. The long-term behavior does not depend on the initial value. That is, suppose there are two solutions, U1 and U2, okay, which are positive, but they are supposed to go the same constant as x goes to infinity. Then what happens is that the distance between U1 and U2 go to 0. So that means that any two solutions have the same asymptotic behavior, or the same long-term behavior. They approach each other. So this means that any solution converts to a particular function, particular solution. Okay. So all solutions go to one solution. So this is said that usually when we talk about the stability of the traveling solution, we must care about this phase shift or this kind of thing. But this time, because the singular point is given in advance, so no phase shift occurs. So all solution goes to the same one solution. Also go to convert to one solution. Okay, so this is the end of my talk, and thank you very much for your kind attention.
I have some questions. Okay, John.
So I suspect some of the results will go down at least to n equals -1, as long as you swap the sign in the.
Oh, actually,
Yeah.
so M is you're talking about M?
Yeah.
If in the negative case. Yes, some part can be carried over actually. Yes. But I'm not sure about the
I think you can do it.
yeah, I think so, yes.
Yeah. Right?
Even
Yeah,
M
the
equals
algebra works, right?
for M equals 0, it's a logarithmic diffusion equation, and
Yeah.
the negative is a similar
And this
diffusion.
works.
It should work as well.
Okay.
But maybe some technical difference, but that's I require. Later.
The question was asked by John King. Now, I have another question. I have been working years ago on similar problems. Let me explain. See if I understand what you did. So you say that you work from a certain point and you prove that you can get the solution here, no? So this x equals psi of e. And this is x t, right?
Yeah.
And you get the solution here, right?
Yeah.
Now, since the equation is invariant under reflections, you have another thing here, and then you get the solution here, right?
Yeah.
And then you get a burning core here.
Yeah, yes. Yeah.
So you can get for any expanding set of reboundaries, you get something that blows here and is a solution here. And here,
Yes,
right?
yes, you are.
Okay. Okay, this is something that we have been trying to understand with Chassagne in 2003. I think. Now, question is, you can expand and get solutions, but in the core you will burn. Can you do that in several dimensions?
Also, if
So you get like no.
yes, if you the singular point singular set is for dimension one, it's for this possible. The east side is one equal, outside is something this.
Okay. So there's a problem of the burning core.
Yeah, one
The burning core is the only real condition seems to be that it has to be expanding.
yes, if it's expanding, yes.
If it burns, it
burning
burns
remain.
forever.
When it's
There's no-
changing, then actually the solution finds solution.
I mean, I want to make some propaganda for this guy. He was a student of Laurent Veron, right? Okay, and more questions? You're raising your finger. Thank you very much. You get uniqueness
Now there
and
is,
stability.
Yeah. Another vehicle to break about an hour and it's over there. And we resume in half an hour, okay?
Matteo and Goro have been organizing everything, so you should talk to them for all practical purposes. We depend on them for everything. Remember, Matteo and Goro. Okay. It works for until you go to -1. I mean, checking your calculations.